All right, let's.
Yeah, chemistry. Did you ever want to be a culinary artist?
Never occurred to me.
Never had the itch.
In my farthest dreams.
It's a lot of patience. You have to be really patient. That's how we did the
Yeah, my specialty is blowtorch chicken.
Egg on your end.
So I don't quite know how to get from cooking to Centroids. It's a well balanced meal. How's that? So there we go. So Centroids, you probably had a look at these in physics and probably in Calculus 252. We use these a lot in engineering, figuring out balance points for how to pick stuff up, and also so we can design beams and things. So let's have a look at how to find centroids. Page 600 is where we are. Okay, so let's kind of go back to something we've already done here. Let's say we got a bunch of weights here. We have a system of weights. So they're all acting down like weights do, and I added them up there for you, and we got a total weight of 240 newtons here in this system. Okay. Now, let's say we want to figure out one place where we could put the 240 newtons. How far over is that, okay? So where's the one spot we could put this total force of 240 newtons in one location so that it would represent those four forces pushing down with a total of 240, all right? So what we're doing here, we're looking at a resultant, aren't we? Okay, and if you remember how to do that, we want to know where the resultant of our system is. What we would do here is we would find the result of this force system. So we added up all the forces, and they come up to be 240 newtons. And then I took the moment about that origin point, point A there on the far left. And I'm taking each force times its distance from the origin, and that gets me a moment there. Now these are all clockwise, so what I'm doing on this, which I can do, I'm going to call clockwise positive just so I don't put a bunch of negatives in there. That sign convention is somewhat arbitrary. And when I work all that out, I get 12.3. Okay, so what we've got here is that net moment. So I can't make this just a bit bigger there. There we go. So 50 newtons times 0.02 meters. I am in Newton meters here. So 90 newtons times 0.05 meters, which is the 2 plus the 3. And then 60 newtons times 0.06, which is 2 plus 3 plus 1 centimeters. And then 40 newtons times 0.08. 2 plus 3 plus 1 plus 2 gets you 8 centimeters. That's 0.08 meters. When I run the numbers, I get 12.3 Newton meters. Okay. Yeah, I'm sorry.
So, but you didn't show them as all being subtracted on the opposite side of 0, but isn't that what they would really, how you would really write them? Or?
I'm not doing equilibrium here. I'm just kind of getting the net resultant. So what I'm doing here, first thing is I'm just saying I'm going to call clockwise positive, which I could do. I mean, it's the sign convention is somewhat arbitrary. And what I'm finding here is the net moment that these would cause about this point right here. So,
Like, but one of those forces make it go clockwise, and clockwise is usually negative.
yeah, but I'm just saying, I'm changing it. I'm a teacher, so I get to do that. I'm just gonna call clockwise positive. I mean, and like I said, those sign conventions, someone just decided counterclockwise is gonna be positive at some point. There's nothing really magic about it, you know? So rather than having a bunch of negatives in here, I just figured I'd just call it clockwise positive.
It doesn't matter because you've only got things on one side.
Yeah, right,
Moment,
yeah,
right?
yeah, right. So, exactly, I know my answer's gonna be clockwise, everything's clockwise, I don't even really worry about the sign. I guess might be a better way to put it. Okay. All right.
You would need to be more careful with those stuff on the other side, right?
Yeah, that's true, although if that's true. If you have stuff on the other side, you might need to be more careful, but if you decided in your world you wanted clockwise to be positive, it's fine. Nothing, it's no big deal. As long as you're consistent with it, you're fine. Now, I won't do that very often. If you take dynamics from me, I'll do it a lot because we kind of get a little more arbitrary dynamics. This class, I wouldn't generally do it, but everything here is, everything's going clockwise. Just add them up. I just want to kind of keep it simple. Okay. So that was my motivation in doing that. It's not a big issue. It's clockwise and it's 12.3. That's really about all I care. Okay. All right. All right. So where am I going to put this one load that represents the whole system? How will I decide how far over to put that? Yeah, right. There you go. Yeah, you're going to take the moment and divide out the distance, right? Or excuse me, divide out the force, and that will leave a distance. Okay, so the resultant force could be placed, where could it be placed to cause the resultant moment? What I would do, I would take the 12.3 Newton meters and divide it by the 240 newtons, and that would get me 0.0513 meters, 5.13 centimeters. So if I take that, if I were to take those four forces that I've got marked and replace them with one 240 Newton force, I would put that force 5.13 centimeters over from the origin. Okay. And in that location, it would cause the same moment as this system does. So that's where the resultant of this system lies, 5.13 centimeters over from A. Yeah. In a way, yeah. Okay. Yes.
What's the difference between that and pressure? Because the pressure is going to act like forces all the way down a line.
Yeah, pressure usually doesn't. These are discrete forces. There's 1, 2, 3, 4 of them. A pressure would probably be some sort of even pressure all the way across, or it might, have some sort of rise or fall or something. It's probably not this jagged though, A pressure is usually created by something like water or air or something like that. So usually it's got a smoother curve, and it's not discrete. There aren't like this one, that one, that one, and that one. It's a smooth curve. So that yeah. Now, you could go all calculus on this and start, taking the limit of these maybe and start turning it into something more like, like a pressure. But this is more discrete. I got 4 distinct forces as opposed to a distribution. Okay. All right. So there we go. So that's what we're going to end up with. Now let's say I'm going to hang these things from a balance beam. Where would I put the fulcrum so that they balance? So if I'm going to put a fulcrum across, or a bar here that doesn't weigh anything, so that won't complicate anything. So I'll just run a bar here, a weightless bar. And I'm going to hang all these weights from the bar. And I want to know where to put the fulcrum, the balance point for the bar. Where would it go? Yeah, one would hope about there, right? If I do that, that's where it would balance. Okay.
So this is the center of gravity? Or
it is, yeah. Yeah, this is the center of gravity, the centroid, whatever you want to call it, yeah. Okay. So we can use this thing we've been doing for resultants and use it to find a centroid. You find the moments of the object about a given point, divide out the weight or whatever the parameter is you're using, and that'll get you how far over the center is, the balance point. Okay. This is how you calculate a centroid. Okay. You use this resultant process that we just went through. So the x-centroid of this system is at 5.13 centimeters. In this case, it would be center of gravity, I guess you could call it. Okay. So there's lots of these centers. There's center of weight, center of mass, center of volume, center of area. But they're all calculated the same way in the same sort of approach. Okay. All right, so what we're doing there is we just did center of gravity. So we summed up all of the x-bar distances, which were to the weights, times the weights themselves, and we summed those up. That got us our total moment. Then we divided out the total weight. Same thing, and just, that's what we just did. We could do centers of many things. We could do center of area, sum of y bar, or excuse me, x bar. Instead of using a weight, we could use an area and divide by the total area.